Good morning and welcome. I'm Al Karitz, Director of Applications and Support at Electron Microscopy Sciences. I'll be acting as the moderator for this series of webinars. We would like to remind you and ask you to take the time to respond to our brief poll, which will be available during the actual webinar. With that said, we will get rolling here. Electron Microscopy Sciences and Quorum Technologies together have many decades of excellence in sample preparation. Today we present in our first of our series of webinars examining three distinct sample preparation workflows for electron microscopy. Today's tutorial is presented by Dr. Helena Bland, is regarding the use of plasma cleaning to get your samples optimized for the next step in your electron microscopy workflow. Dr. Helena Bland joined Quorum Technologies as an application specialist in 2024. She completed her integrated master's degree in chemistry with biology and medicinal chemistry at the University of York. Following her degree, she worked as a research assistant at the University of Helsinki, specializing in carbohydrate synthesis. Helena completed her PhD in chemistry at the University of Sussex, where she synthesized leptin peptides and investigated their impact on aggregation of amyloid, beta amyloid and tau amyloid using transmission electron microscopy. In her role at Quorum Technologies, Helena delivers technical expertise and guidance to the company's global customer base. It works closely with users to understand their specific workflow requirements and recommend tailored application-based solutions. Through her support, Helena helps customers optimize their performance of their systems, adapt to evolving scientific and needs to achieve reliable results. High quality results is the goal. Without delay, I give you Dr. Helena Bland.
Hello, thank you so much for that lovely introduction, Al. As Al mentioned, this is going to be our first session in a series of webinars about sample preparation for electron microscopy. As Al mentioned, my name is Helena. I'm an application specialist at Quorum Technologies, and EMS have been Quorum have been working together for over 20 years now, specializing in electron microscopy sample preparation. Before I start talking about plasma treatment, I just wanted to say a couple of things about what we do in electron microscopy sample preparation. So we have four main streams that we work with. So one is critical point drying, so for the dehydration of high moisture content samples before SEM. We do carbon evaporation and sputter coating systems for the coating of non-conductive samples for SEM. We do cryo preparation systems for the rapid freezing of samples prior to going into SEM. And finally, and what we're going to be focusing on today, which is glow discharge and plasma treatment systems for the cleaning and activation of surfaces of samples. So this is just a brief overview of what we're going to be covering in the webinar today. I always like to start off by talking about the sort of principles behind the technique we're doing in the first place. So we'll start off with what is plasma treatment and then why it's so important in electron microscopy applications. And then we're going to move on to talk about some specific applications in both transmission electron microscopy as well as scanning electron microscopy. Finally, we're going to finish off by talking about some of the frequently asked questions that we get at Quorum and also at EMS, and then opening up the floor to questions from our attendees. So just to introduce you to plasma. So plasma is our fourth state of matter, and it's composed of ionized matter that is electrically conductive and highly reactive. And for us, it's very, very useful. So when we're thinking about plasma, If we think about a plasma treatment system, this is just a representation of a chamber. Our chamber will be attached to a vacuum pump, so we'll put that chamber under vacuum, and then we'll have a gas inlet. So some systems can have single inlets, so we're just putting one gas through the system, and some systems can have dual gas inlets, but just for this diagram, I've only drawn one. So if we were to do plasma treatment in air, we would have a bunch of nitrogen and oxygen molecules coming into our chamber, and we then apply a voltage to that chamber. This will result in the collisions of free electrons into our molecules, which will result in the production of ions. It's this collection of ions and electrons that we know as plasma. And plasma is primarily used for two different things. So the first one is cleaning. So that's removal of contamination from the surface to help reduce noise and to improve coating quality. And also the activation of surfaces. So that's to change the hydrophilization of the surface, which can help to improve adhesion to that surface. When we're thinking about doing plasma treatment, there's a few things you want to consider before you start plasma treating your samples. And the first one of that is selecting the correct process gas. So there's lots of different gases you can use for plasma treatment, but there's different reasons why you might use different gases. The first one I wanted to talk about is argon plasma. So argon plasma, when we're using argon, we're generating argon ions, and they are bombarding our surface. And this is a form of physical cleaning. So we're not actually having any sort of chemical reaction going on. The argon is simply bombarding the surface, so it's able to remove anything that's weakly bound to the surface of our sample. This is a very gentle type of cleaning because it is just a physical cleaning. So it tends to be used if anyone has particularly delicate samples. On the other hand, our oxygen plasma behaves very differently. So in our oxygen plasma, we're going to have oxygen radicals, which are going to react with the surface of our sample. So this is going to oxidize the surface to produce hydroxyl, carboxyl, carbonyl groups on the surface of our sample. And this in turn will make the surface more polar and also more hydrophilic. So with oxygen plasma, we're not only cleaning the surface by removing any hydrocarbons on that surface, we're also hydrophilizing the surface as well. What a lot of people choose to do is they will combine argon with oxygen plasma in order to get the effects of both the physical sputtering as well as the chemical oxidation with the oxygen plasma. And this is really great because you can fine-tune how much argon and oxygen you might want in your plasma to depend on the type of sample that you're cleaning. So if you have a very robust sample, you can probably have a higher concentration of oxygen, whereas if you're working with something very delicate, a biological sample, for example, then we might consider having, say, 95% argon and just 5% oxygen. So we're not at risk of damaging that sample. There are some other options. So you can use just air in order to generate plasma. So air is kind of similar to oxygen. Well, I have some of the effects of oxygen because we have oxygen in our air. So we will see that oxidation on the surface, but we'll also get effects from our nitrogen, where we'll see nitrogen functional groups on the surface of our sample. The major issue with air plasma is that it is, of course, harder to control precisely than it is with using a purified gas. But it will have a similar effect to using oxygen, where we'll still hydrophilize the surface, and it also is able to clean the surface of our sample. We then have nitrogen plasma, which is a slightly more gentle way of hydrophilizing a surface compared to oxygen. So you have an oxygen-sensitive sample, then nitrogen plasma might be something that you use. And then finally, we have hydrogen plasma, which is not commonly used in electron microscopy applications. And this is because it is a very harsh way of cleaning the surface of something. So it's typically used for cleaning metals. And it can also, interestingly, decrease our surface energy and actually make a substance more hydrophobic, which is not typically what we're wanting to do for biological samples. Once we've selected a process gas, we want to think about the kind of power that we're putting through our plasma treatment system. We would consider 1 to 30 watts to be a low power, and this would be a very gentle plasma cleaning and activation with minimal surface damage. So this is perfect for soft materials like polymers or anything with fine structures. Then increasing the power, sort of moderate power, would be between 30 and 100 watts, and this is ideal for general SEM routine preparation. So it's really great for removing hydrocarbon contamination, and if you've got a sample that isn't super delicate, then you'll get a much faster rate of removal of contamination with the moderate power. We then have high power where we're going above 100 watts, and this is very aggressive cleaning and etching of a sample. So this would be ideal for metal cleaning such as stub cleaning and also sample holder cleaning as well. When we've decided what kind of gas we're going to use and what kind of power, then we need to think about the time. And this is fairly intuitive, that you want to balance your contamination removal with your sample preservation. So you would think that a longer time and a lower power would be a more gentle way of cleaning something with lower risk to the surface. But if you do have something that's particularly contaminated and you want to rapidly remove that contamination, then you can do a shorter time with a higher power. I just want to introduce you to the systems that we have available at Quorum Technologies and Electron Microscopy Sciences. So we effectively have 4 different plasma treatment systems that sort of fit into 2 categories. So the first 2 here are the HBT 100 and HBT 200. And they are so named because the HBT 100, the maximum power is 100 watts, and the 200, the maximum power is 200 watts. They do also vary in the sample size that you can use in these systems. So with our HBT 100, we have a slightly smaller sample size chamber compared to our HBT 200. So you can get slightly larger samples in the 200. Both of these are available with either single or dual gas inlets. So if you are wanting to combine, say, argon and oxygen to sort of fine tune your plasma treatment, then you can get a dual inlet system to be able to do that. Both of the systems have this easy-to-use touchscreen, which can be used to make customizable recipes. So that's up to 4 recipes where you can change the time, you can change the power, and you can change the gas flow and which gases you're going to be using in the system. Our other 2 systems are similar in that we have a 100-watt and a 200-watt version. And the main difference, as you probably saw in the image, is it's got this additional feature here. So this is our TEM holder port, which can be used to hold TEM grid holders. And this can be designed for compatibility with all the major TEM grid holder manufacturers. So if you have a Hitachi, a Joule, or a thermo system, you can have it designed so that your TEM holder fits perfectly in your port. This means that you can use the system not only to prep SEM samples, but also to clean your TEM holders as well to make sure that they're very clean for when you're doing your imaging. In addition, we have an option for a vacuum storage module. So this would be placed on top of the system. And it means that after you've cleaned your TEM holder, you can then keep it in the vacuum storage to keep it under vacuum and keep it clean. So those are the 4 systems that we have at EMS and Quorum. And now to go on to some specific applications that we can use plasma treatment for. So plasma treatment in TEM can be used for removal of hydrocarbon contamination, cleaning of TEM holders, like we've seen in the previous slide, improving wetting and dispersion, fine-tuning carbon support films, and also to improve the reproducibility of our imaging. So this is a really nice example of the removal of contamination on TEM grids. So this is actually a STEM image, but it shows a lacy carbon support film that's been coated with carbon, platinum, and chromium. And you can see there's a very small amount of hydrocarbon contamination on this particular film because it's actually one that was plasma cleaned and then allowed to become contaminated again just by sitting in air and the hydrocarbons building up on the surface. So you can see on the left image that we have these 2 dots present, and this is our hydrocarbon contamination. And then you can see when we've done our plasma treatment, these 2 dots are no longer there, but the structure looks exactly the same. So we've not damaged the lacy carbon support film in any way. We've simply removed this contamination from the sample. We can use our plasma cleaners to clean our TEM holders. And this is really important when you want to think of long-term maintenance of your holder and your instrument performance. So obviously, if we have a clean TEM holder and we're putting it into our TEM column, we're likely to improve our vacuum quality, reduce the risk of cross-contamination, and we can also remove any hydrocarbon contamination that might have built up on our holders. So it's really good sort of general practice, good practice to be cleaning your TEM holders. I mentioned that we can fine-tune preparation of carbon support films. So when we are using TEM grids, we can either coat them ourselves or we can buy pre-coated TEM grids. So with this carbon-coated grid, we can see that with no plasma treatment, we have this carbon film on the top. And we can actually etch away that carbon film gradually using a mixture of argon and oxygen plasma at 50 watts. So you can see after 90 seconds, we're starting to etch away the top of that film. And then further, we've completely etched away part of this film. That's really useful because it means that we can either sort of etch away a film completely and recoat if there's been an issue. If you do coat your own grids with carbon, then you'll know that thickness is super important. So you can make a carbon coating potentially a little bit thinner using plasma treatment. And then you can also, if you pre-buy your grids already coated, it means that, so typically they've been stored in places where they wouldn't, where they might get hydrocarbon contamination, and you can clean the top if you used a much gentler power. So if you say use 10 watts, you could just remove the hydrocarbon contamination off the top of that. Finally, it can be used for wetting and dispersion. So I do have a slide later in the presentation to go through the differences between glow discharge systems and plasma treatment systems, but I'm going to highlight it a little bit here. So if we just have a water droplet and we put it on the surface of a glass slide, then what we'll see is that water droplet is going to sit on top of the slide. Then if we use plasma treatment, if we're using either air, oxygen, or nitrogen, we're going to be functionalizing that surface with either hydroxyl, carbonyl, or amine groups, depending on what we're using. And that's going to make the surface more polar and more hydrophilic. And that's why we're able to get a much better, adhesion of our water to our surface. Now, we actually use that technique with our glow discharge systems at Quorum. So it's the same thing where we're using plasma in order to hydrophilize the surface of a TEM grid, but you actually can use a plasma treatment system to do the same. So a plasma treatment system, naturally, if you just do either in air, in oxygen, or in nitrogen, you will make the surface more hydrophilic. So you can potentially hydrophilize TEM grids using a plasma treatment system. The key difference is that if you have a specialized system for TEM grids, such as the Glow Cube or the Mini QGD, you'll be able to fine-tune these properties a little bit better. And I do have a slide about that later, so I'll discuss it in a bit more detail. Then moving on to SEM, we have a few applications in SEM as well. So removing hydrocarbon contamination again, improving adhesion of metal coatings, cleaning our SEM accessories, and also improving our reproducibility of imaging. So this is actually just an example with a silicon wafer. I went for a silicon wafer because it quite clearly shows the difference really nicely. So it's a silicon wafer that's been coated with gold. And on the left-hand side, we've got no plasma treatment, where we're seeing this characteristic contamination square, which is where our hydrocarbons are being damaged by the beam, which is resulting in polymerization of those hydrocarbons, which forms these squares on our images. Now, with the same conditions, with our plasma treatment, before I've put that gold coating on, we can see that we're able to, and this is even at a higher magnification, not have any problems with our hydrocarbon contamination. Plasma treatment is also really great for improving the adhesion of metal coatings. So when we sputter onto our non-conductive samples for SEM, we can actually use plasma treatment to make that coating a much better coating. So this is because when we've got a more uniform layer to coat on, so we've removed any contamination from the surface, it means that we can get a better nucleation of metal film, so we've got a more uniform coating across. It also enhances mechanical adhesion, so we're reducing the risk of the coating flaking or peeling off from the sample. And finally, it actually makes a better conductive layer because we have a continuous uniform layer rather than an interrupted layer, which means we can help to minimize charging by just doing some plasma treatment before we do our coatings. You can also use plasma cleaners to clean any of your accessories associated with electron microscopy, so sample stubs, sample holders and adapters, tweezers, and also mounting tools. You can use a very high power on these types of materials because they are metal and they can withstand quite a high power. And it just means that you're making sure that you're everything you're using for your electron microscopy is nice and clean and is not going to cause any contamination. So I said I was going to finish by talking about some of the frequently asked questions that we get at Quorum and at EMS. So the first one of that is, what is the difference between plasma treatment and glow discharge instrument? There's a few differences, so they work on the same principle. In both, we're generating a plasma in order to modify a surface. So the first difference is the sample size. So with a plasma cleaner, we typically have a much larger chamber. So we're looking at larger samples, whereas with a glow discharge system, they are designed specifically for TEM grids. So we tend to have smaller chambers because TEM grids are, of course, very, very small. So on the right here, I've got our GlowQ Plus system, which is used for surface modification of TEM grids. With a plasma cleaner, I've described it as moderate control. Obviously, you have a lot of control. You can change the process gas you're using. You can change the power you're putting through the system, the gas flow rate. But what you don't have control over is you can't control polarity. So with a glow discharge system, you can either apply a negative polarity or a positive polarity to create a voltage gradient across the system. So you can basically either tune it so that you've got more ions going towards your sample or more electrons going towards your sample. So basically what you can do is you can have better control about how hydrophilic or hydrophobic your surface becomes, as well as how polar you can make that surface. You also have options for doing in-chemical glow discharge as well, which is another way we can functionalize a surface, and you wouldn't typically do that in a plasma cleaner. In general, plasma cleaners are a lot higher power, and then a glow discharge system would be up to around 30 watts. So to sort of summarize, a plasma cleaner is best for general cleaning and general surface application. But if you are activating the surface of TEM grids to make your samples adhere better to the grids, then you want to be considering getting a glow discharge system where you've got a much finer control over the grid surface properties. The next question that we get a lot is, what's the difference between a kilohertz and a megahertz plasma cleaner? So at Quorum, we sell kilohertz plasma cleaners, but you may be aware that megahertz plasma cleaners are also available at other vendors. And the key difference is that with the electron energies inside a kilohertz plasma cleaner are much lower compared to a megahertz plasma cleaner. And this means that the sort of potential damage of samples is much lower in a kilohertz plasma cleaner compared to the megahertz, which means that kilohertz plasma cleaners are more suited for sensitive samples and gentle cleaning. Whereas with a megahertz plasma cleaner, that is more of a hard etching of thick contamination. So typically we'd see megahertz plasma cleaners in industrial environments where materials are being either etched or a lot of contamination is being removed from a sample, whereas the kilohertz plasma cleaners are better suited for electron microscopy. I also get asked quite a lot, how long does the plasma treatment actually last? So after we've done our plasma treatment, we will gradually the surface will return back to how it was before. So if we've activated the surface by making it more hydrophilic, this will then over time gradually return back to where it was and become more hydrophobic. And also if we've removed the hydrocarbons, if you just leave something sitting in air, it is going to gradually become contaminated again with those hydrocarbons. So how long does plasma treatment typically last? Typically, it can last up to about 2 hours. However, I'd always recommend, if you are either loading a sample onto a TEM grid or you're cleaning a sample before you do a coating on it, that the surface modification itself is going to be best in the first 5 minutes after the treatment. So if you are going to be loading a sample onto a modified TEM grid, then you want to load that sample as soon as possible. If you're going to be putting a sample in a coater and you've just cleaned it, then you want to put it straight into the coater, because over time that plasma treatment effect is going to decrease. But there's obviously a few factors that can influence how long the effect of that plasma treatment will last. So for example, the environment you're in, obviously if you do some plasma treatment and you put it under a vacuum, it's going to last a lot longer than if you're in a clean room, which is going to last longer than if you're just working in an ambient lab. The material as well will also affect how long the plasma treatment effect lasts. And finally, of course, the plasma treatment conditions you use. So I mentioned earlier, if you're using a very high power, you're doing a very aggressive clean on the surface of your sample. So this will last longer than if you are doing a very gentle clean. So that's everything from this presentation today. I did just want to point out our sessions that we've got coming up. So on May 27th at 9 a.m., we will be doing our second session, which is on thin film coating for ultra high resolution EM imaging and analysis. And this is going to be focusing on both sputter coating as well as carbon evaporation and how to optimize those particular coatings for particular samples. And then our third session is going to be held on June 17th at 9 a.m. And that is focusing around cryofibsym techniques for lamella preparation and volume imaging. If you'd like to have any more information about these webinars, we've got the link below. And I'm now going to open up the floor to any questions that you might have. So I'll just stop sharing the screen. Oh, Al, I think you're on mute.
There we go. That's one way to keep my big mouth shut. Yeah, thanks for that very informative session, Helena. Lots of good information there. We do have a couple questions. First of all, what system would be best to clean a 12-grid stem holder for SEM? Now you're
I'm on mute now. A 12-grid, it depends how large the holder is, but if it's similar to a TEM holder, then we can do a customized version. I'm just going to quickly see what the 12-grid stem holder looks like.
I imagine it would be manufacturer specific.
Yes, it probably would be. So, I mean, the sample chamber size is for the 100. Let me just double check before I make something up. Is 90 by 250 millimeters. So it just depends on the size of that holder. So if it is, so the HPT 100 is 90 by 250 millimeters and the 200 is 130 by 250 millimeters. So it will depend on the size. I guess with a stem holder, you might be able to just put it into the chamber itself and just sit it on the tray rather than having a port for it, because the ports we do for the TEM holders.
All right, thank you. Next question. Would you comment on plasma cleaning, glow discharge versus UV03 cleaners in regards to surface activation and wettability? You're muted again.
Yeah, so with our surface, with our plasma treatment and glow discharge, so for cleaning, I would primarily use our plasma treatment, and then glow discharge would be primarily used for TEM. When we're doing our UV cleaning, we're of course using ultraviolet light. So the sort of limitations of our UV cleaner is it's going to be a little bit slower than our plasma treatment, but it is good for removing organic contamination. The only thing is with UV is that it's quite, so it's surface only. I guess it really depends on what the sample is, because the treatment as well can affect what kind of coating that you can put on the samples as well, and the type of samples that you're doing. So it will depend. But I'm happy to send over some information about that after the webinar.
Okay. Are there any more questions from the audience? Well, I would remind everybody to join us next time for the next webinar. And I thank the participants who hung out to the end. I hope that the use of time was well rewarded. If you have any questions, there's certainly links you can get in contact easily with myself or Helena, and we can support any of your application questions, as well as provide further information on any instrumentation that EMS and Quorum provide the electron microscopy community. Remind you real briefly to please participate in the survey. That helps us out in formulating what topics and what interests you have, so we may serve you better. I believe that will conclude our webinar for the day. Thanks very much.
Thanks everyone for joining.